funnel. It's funnel time, bro. The big suck.
My tube is not very consistent.
Yeah, not consistent too. That's gonna mess up the Bernoulli's principle.
What's the first one? Too much chocolate milk.
The queen is dead.
People won't shut up. The queen's finally dying.
I know. Wait. God didn't save the queen.
I just like the video saying about a Megamind.
There's a queen.
Oh, that guy, yeah.
All right. This one example in the book, page number 62, example 2.5. And what it says, it says we have a cone that is connected to a U-shaped tube. And we always, in this sort of problem, we always assume that this glass is so clean and wide that the surface friction, because there are some surface tension forces that keep this fluid a little bit unbalanced. We ignore all of those. So the only forces on the equilibrium of this fluid in the static form come from the gravity. Right? So this configuration, we have a U-shaped tube connected to the cone, and then here we have mercury, and the density rho Hg is given, and then we put a little bit water on it, so this height will go up and down a little bit, and then we put this original a little bit up, and then we put a little bit more oil on it, and then it goes in this configuration, right? And we want to compute H, the surface height between the mercury and the oil, right? And this all the rest of all this density is given, the other height is given. You can measure that in the lab. You can take your
4.9.
So what should I do? You compute that height, H. Well, you can use. I don't want this to dry, none of them dry as fast. You can use the relation we developed that was P is equal to rho dH, or simply you can call this gamma H. And you can write this between any 2 points, right? Like you can't write it between here and A directly, even though the H and J is same, G is same, but rho is density is changing. So you have to write this relation between 2 points in a uniform constant density field. So here is what I can do. One way is to say, look at this point C, right? According to that formula, the pressure only depends on the height and the density of the column of water. So that means because this C is in mercury at both part of this U-shaped tube, I can say PC here, call this point C prime, is equal to P, so P at C is equal to P, C prime. The pressure at these two levels, there are levels, right? The pressure is just same. So what can I write for PC? The pressure at this point. The pressure at this point is pressure from here to here, plus pressure from here to here, plus atmosphere pressure. Let's say this is exposed to atmosphere. So the P0 is right here. So P at C, instead of that, I can write P0 plus the pressure at B, which is rho oil times G H between A and B, plus the pressure within this point, the common rho at water, H, G, H between B and C. This is the total pressure between come from atmosphere, goes all the way to C. So this is PC left hand side. It should be equal to the pressure in the other point in the same fluid. There's the same pressure. So that's going to be P0. You see this end is also exposed to atmosphere. So pressure here is also the surface pressure P0. P0 plus the pressure comes from the height of this mercury column, which is the density of, we can call it Hg times H, and this height. Let's call it H bar, this height, right? Times H bar times G. Right? So what is H bar? I can write for H bar is equal to this length minus H. You see that from here? So you can, for H bar, you can write that P0 plus rho Hg times G instead of H bar, you can put 0.7 minus H. So immediately you see that P0 cancel out. Most of the problem we solve, the gauge pressure or the atmospheric pressure, they will cancel out. So we always, that's the reason they talk about this terminology, gauge pressure, extra pressure, delta P, because that thing usually cancel out most of the practical problem. Now let's plug in the number. So for the rho of oil, what was the rho? You have to put it here. The rho of oil is 8. So for that, we put 880 times 981, and then HAD, which is 0.3. You want to make sure this all is in meter, right? Plus raw water, which is 1,000, hopefully. Yes. G 981 times HPC, which is 0.4, is equal to, well, this cancels out, then you get rho of mercury, which is 13,550 times 981 times 0.7 minus H. One equation, one unknown, a very simple equation. You get a constant, you solve for H, and if you solve for H, you get H is equal to 65 centimeters. That's
Not too bad.
yeah. That's one of the application of the U-shaped tube to get the pressure at different point in the quiz we had to get the density of the container. Like if you have fluid in a container of gas, if you want to probe the density, just like a multimeter. You know, multimeter, you put it at a point and you get the voltage. Here with the U-shaped tube, you can get the pressure, you can get the density, just like a multimeter.
So does G usually cancel out too, or is it just for this problem?
Always put G, because sometimes you may have one end is not exposed to the atmosphere, and the pressure is given just like the quiz. So what I would do, I would first do the symbolic this way. If G cancel out, just get rid of it, don't put it in computation. Otherwise, you just put it in the calculator. Don't always say G cancel out. Next problem. Now, what I'm going to do, I'm going to work on the hydrostatic forces. So force, hydrostatic forces and moments on object. obviously, one of the most frequent application of this is dam design, like bridges, dams, water reservoirs. So you have a huge amount of water sitting behind a dam, and you want to know how much force you have, right? If you don't know how much force you have, you don't have the loading. So if you had a structural design course, if you don't have loading, you can't even start it, right? So in order to get loading, one thing we can do, we can just use this relationship obtained to model forces on submerged object. So let's say this is your, for example, a plate, and I want to draw both 2D and 3D version of that. So 3D version, let's say you got an arbitrary shaped object, but for the moment it's just that is submerged in the water. And let's say that's the height that the water, this is the surface of water, so this is P0 atmosphere, and then the water starts from here. And now let's have this coordinate system. Let's have our y going this way. So that's your y coordinate system, and your x going this way. And I can put this anywhere. You don't have to put it at a particular point in an object. I can put it anywhere, just like here. So this direction, your x, this direction is your y, and obviously any surface we had in vector statics, there is a centroid. Let's say this is the centroid. That's my centroid right here. So you show you centroid with this particular symbol, and also you have a coordinate system in your centroid, x bar, y bar. It's just a coordinate system, right? So now, if you look at it from the side, so look at it from the side here, then you see that. If I want to draw a 3D plot here, then you see this plate, and that's the surface, 0. And now, starting from that point, is your y, and then the x is going this way, outward the plane that you don't see, but you only see y. And now the objective is find the forces acting on this plate. So what should I do? Well, if I go back to my basic definition of the two-dimensional element, right? You remember that we did in mechanics of material. We had sigma x, sigma y, and then there was a tau xy, just like that. This element is in equilibrium, it's not accelerating. So all these forces from the stress distribution should be in balance. Now in this case, for shear stress that we had in last class, what can I say about shear stress on that plate? That plate, assuming is just in equilibrium, it's not moving. It's constant in space. It's fixed. What can I say about shear stress of fluid acting on the water? Go back to the relation for shear stress. What was shear stress? Tau was mu times the gradient of velocity, right? What's the velocity? 0. What's the gradient of velocity?
0.
So the shear force is 0, right? In fact, if you draw your element, any element on the surface, this is submerged in water, right? Let's say water is only on top of it. There you go. Here, the bottom is, there is nothing, right? It's empty, vacuum. So the water is right here. So any element you pick here in the water, if you draw a 3D for that, the shear force is 0, so you only have the sigma, the normal stress. And what's that normal stress? Pressure, sigma, pressure. We had this before, right? So if I want to compute the loading on that, there is nothing coming from the shear. So later on next chapter, not only you have pressure, we also the object is rotating, so we have some sort of gradient, shear. Then we have to also add the effect of shear, the viscous term. They call it viscosity, viscous term. But here, there is no movement, therefore shear is 0. So the only thing I need to do is to deal with pressure, right? So let's do that. Let's take an element here on the surface of this object and draw a 3D for that. If you do that, you see that, you're gonna get the forces, let's say dF, infinitesimal forces come from the only pressure, no shear, acting on a plate. And it starts from here and ends here, right? What can I write for dF? Well, dF is what? Use P. dF is what? P dA. Why? Well, what's the definition of pressure? Pressure is force divided by area. If you shrink your area to infinitesimal dA, then you get dF over dA, right? Then you solve for dF is equal to P times dA. That comes from there. So that's my equation for dF. How many dF do I have? 1 dF, 2 dF?
Infinite.
Infinite. So you have to sum, if you want to find the resultant force, you have to sum all this dF here, which I'm doing it here. So the F total in the normal to the plate is sum of all this dF to infinity, right? What do I mean by sum infinity? Integral of dF. Integral over where?
The area?
The area. You see the entire area of this weird plate. Now you can see in your calculus book, you had complicated shapes, two-dimensional shape, and they ask you to evaluate two-dimensional double integral over those shapes. And you always wonder, why do I need that as an engineer? Because of that. So integral over area of dF, which you can show that by this double integral, right, of dF, and then you can substitute the definition of dF from this relation. So you get double integral over this area, P dA. Now what can I do for P, the pressure at any point here? Well, let's say this angle is theta. Let's say this angle is theta. And let's say this is the height of that point element, H. And let's say the location of that, because my coordinate system is in my y, it starts from the surface, so from to here is what? Positive y. See that? So what can I write for P at this point? Well, I go back to my lecture from the last class. P is gamma H, right? So I can write that in double integral P rho G, right? For gamma times H times dA. Now what should I write for H? Look at this triangle. Look at this triangle. If I draw that triangle here, you see that? This is your H, this is your theta, and this is your Y, this side. If I write sine theta, I get what? I get H over Y. And if I solve for H, I get Y sine theta. Then I substitute here. I get what? Double integral gamma. For H, you put Y sine theta then VA. In these terms, both theta, sine theta, and gamma, they do not depend on xy. They do not depend on double integral. So what can I do? I can just take them out of the integral. So you're gonna get the resultant force. I'm gonna write here the F total is equal to gamma sine theta. I bring it out of the integral. Double integral y dA. All right, guys. What did I have for double integral y dA in vector statics? These things are all chain together, so they're connected together. What can I write for y dA? Double integral y dA.
R dr d theta.
No, that's the dA for cylindrical coordinate. We had the centroid. Remember the definition of centroid? X bar was what? Integral x dA over
Is this like the DH?
yeah, double integral.
Stuff?
Say it again.
Is that like the DH cubed over 12 stuff?
pH.
Where like it changes for reg x and
Not quite the same, but close. Y dA is equal to A times y bar. What was that? The y location of centroid. Right? We had in vector static, and also A times x bar integral x dA. We had this vector statics chapter 3. Right? We had centroid. Now you have the book, right? You can go back and review that because we need that in this course. We need this, right? So for that, you can say you can use this relation here. So instead of y dA, we can put y bar, the location of centroid times A. Why do we do this? Why do we try to get something in terms of the centroid and moment of inertia 1? Well, we want, as an engineer, we want to avoid double integral as much as we can. So if somebody give me a very complicated geometry like that, instead of doing double integral, which is one way, I mean, the exam I may ask you to do double integral. Because one section in your book, it says the method of double integral. So you have to learn it. But in practice, we don't want to do double integral because it's time consuming. We go to the handbook and we use the moment of inertia and centroid to get the information. So we try to convert double integral into the centroid. That's the reason instead of that I put y bar times A. Because I can get centroid from handbook. Instead of doing double integral, I can go to the handbook and get the centroid. So for that, I write what? Gamma sine theta times y bar times A is equal to. What can I write for y bar times sine theta? Look at this triangle again. Y bar sine theta is what? H bar. So the final answer is gamma H bar times A. That's it. So first result, this is my first result for today. The force on this, the resultant force, right? The net force, F total, is its value is equal to, its magnitude is equal to gamma H bar times A. What does it mean? What is my H bar? Look, H was the depth at any point on the surface of this plate, right? H bar was the depth at the centroid. That means if you want to find the net resultant for this force, for this plate, find the centroid and then see how much is submerged. Find the height, the depth of submerged centroid. And then multiply that by area by gamma. You get the total force. normally practical engineering, it works for 90% of problems. In fact, if you have the centroid, it works for 100% of problems. But the reason that I say it works for 90% of problems, because 90% of problem engineering, you either have a rectangle or triangle or a circle, right? If you want to design like a submarine or something submarine, you have all these simple shapes. You can immediately get the centroid and HR. Sometimes you have curved geometry, and also we're going to have something in the test. In the exam, we're going to have curved geometry. In that case, you can't do this because you don't have the HR. If I give you HR, yes, you can. This is always valid. But in that case, if you don't have HR, you have to go to double integral. And you go to it's called section for a double integral method when you have curved geometry. So anyway, so this is the first result we get today. The second result, the question is, okay, I know how much force is acting on it, but the question is, at what location this net force is acting on? That's the question. At what location on this plate is net force is acting on? You know, I can, without even solving the problem, I can say intuitively, I can say I can replace all this tiny EF with just one resultant force, and I know the magnitude. And it may go through the centroid, right? If you go to intuition, it may pass through the centroid. But that's not the case. It will pass through the centroid, but just a little bit below the centroid. So there is a shift. And we try to find that. So in order to find that, we need to, again, write the equation of equilibrium, just like I did before that, and apply the equation of equilibrium and simplify the result and see what I get. The reason that I'm showing you the proofs like that is you have to really understand under the hood. You really should understand the core of it. It's not like vector static that I can just simplify, give you tricks, and then you can answer the question. In the question in test will be heavily based on the concept that I teach here, the insight. And I don't want to trick you, I don't want to give you a hard question. All I do is just give you the question from the book. So either we have to just simplify things and say, use another book, which is basically, there is no other book simpler than that. This is the easiest book. The other one is a book written by a guy named White, and that one is twice harder than this. So unfortunately, I know that you guys get bored today. I know that. I know that, and you're right. You're right. But unfortunately, in order to get your undergraduate degree, you have to deal with this. Unfortunately, right? You understand what I'm trying to say? I can just put a problem here, bunch of number, pound, force, inches, plug in the number, but that's not going to help you to solve the problem in the test. In the test, you really should understand how this equation is applied, to apply it to the actual problem. But there's not going to be any formula. Even if you bring your cheat sheet and say you write all the formula in the book, you can't still solve the problem in the test. I'll guarantee. Right? You really need to understand it. So, unfortunately, we have to go through this mathematics and derivations, and not a good idea for engineers, but we have to put up with it. All right, so in order to find the location of this force, I said it's just below the centroid. How do I know that? Well, he went to the lab, he manufactured the plate, he put it in the water, and then he put like a razor to make it balance, because it doesn't stay in equilibrium. And that razor point that he put, it turned out it was a little bit below the centroid, so that this thing doesn't rotate. And he realized, oh, the force is not going to the centroid, it's a little bit below that. And then another person, like 50 years later, a mathematician tried that relation. that you're right, the force is not passing through the center, it's a little below because of this reason. And now here is the reason. If you write sum of the moment about this point, right, if you assume that you replace all these three F total at some point that we don't know why, let's say y tilde, that's what I'm trying to find, y tilde, let's say from here all the way to here, let's say this is your y tilde. Y tilde is the location of the resultant force. The resultant. I want to find what right? So if I put a resultant force, which I know the value, what's the value of the resultant force? At a particular y tilde, the moment coming from there should be equal to the moment coming from the all infinitesimal forces. Sum of moment should be the same in order to, I say that they are equivalent. I can replace one for the other. Mathematically means that the moment coming from all df, all the infinitesimal force must be equal to moment of the resultant. It's just simple as statement. Now, what's the moment coming from the all infinitesimal forces? Each one is df, right? And each one is acting at the location y. So the moment is what? Y times df. And I have to sum this. How can I sum this? Double integral over area. This is the net resultant moment come from all infinitesimal df. This must be equal to the moment come from F total times y tilde. F total times y tilde. Now that's what I'm trying to find. The location of the net force, right? So let's go ahead and expand that for df, just like I had before. I can write gamma. I first write p dA, and then for p, put gamma h, gamma h dA, and also for h was what? Y sine theta. Y sine theta. So gamma rho gh, or p, I'm sorry, F is equal to PA, P is equal to rho g or gamma h, and h equal to y sine theta. So if you fully expand that, the left hand side is going to be integral over area y, and then the final result gamma y sine theta times dA. Right? So that's the left hand side. The right hand side, what do we get? What was my F total? F total, its magnitude was what? Gamma times h bar times A. Gamma h bar times A. That's your F total times y tilde. And I'm trying to solve for y tilde. So that means y tilde is equal to this guy, whatever it is, divided by that guy. Right? So let's do that. That means solve for y tilde, the location of resultant force is equal to that term, bring gamma sine theta out, right? So you get gamma sine theta, double integral, y squared dA. This is your left hand side, gamma sine theta, double integral, y squared dA, divided by this guy, which is gamma h bar A. Now, as an engineer, once again, for simple geometry, we have handbook, right? We don't want to compute everything, so I have to convert that to simple handbook problems, like either rotation of centroid or moment of inertia. These were two concepts that it was handbook or tabulated version of double integral. So what can I write for that? What is that? What is this guy? Can you tell me? Who's ever? What is that?
Y bar times A squared.
No. Look, this is the side view of this. That means I'm looking from here. So, starting from this y, I do y squared times dA integral. What was the square y? Not y dA. What was the square y dA? That kind of integral. What did we call it?
For spherical, isn't that a sine squared thing?
No, there is a term that we used to call it in vector statics. Moment of inertia. Who said that? Who said it? So that's y squared. You see, y dA gives you something. Y to the first power. To the second power gives you moment of inertia. So this guy is the moment of inertia with respect to what axis? With respect to this axis, right? Because that's the point. That's my x coming from this. I compute the integral with respect to that, right? So y with respect to x. But look, what can I write for I with respect to x? Y with respect to x is what? You remember parallel axis theorem? Hat. Parallel axis theorem. You have that. This was it was the stating Ix is equal to Ix bar plus a d squared. You remember that? I'm pretty sure you do. I used to give this in tests. So I have the moment of inertia with respect to the centroid. Always the one in the handbook. The one that you see in the handbook is for Ix bar with respect to centroid. It's not with respect to any location like x. But I can find a relation. The one in the handbook plus the area times the distance between these two parallel axes squared is equal to Ix. So that's what I'm substituting here. So let's instead, for Ix, let's make that equation a little bit more useful. First of all, before I simplify that, you get rid of gamma. So you get this relation, you get sine theta. So instead of this integral, I write Ix bar, right? This is just Ix, right? I write Ix bar plus the area times d squared. But what is d? Can you tell me? Yeah. The distance between this point and the centroid of this point. Right? Let's say the centroid in this figure, let's say this distance from this point and the centroid. Let's say call this what? Y bar. That distance. That means that distance is from here to the centroid. Let's say centroid here. That distance is y bar. If you look at it from the side. Right? So that's going to be y bar squared. So instead of d squared, I just say y bar squared. So Ix bar plus a times y bar squared. Right? So sine theta that times that divided by h bar times a. Now, what can I write for sine theta? Sine theta was, just I did it before in order to get that relation. Yeah, sine theta was y bar times, you see y bar times sine theta is h bar. Y bar sine theta is h bar. Look at this triangle here. You see this is your h bar. This is the triangle. So if I draw that triangle here, you get h bar That theta, and from here to here is y bar. So y bar sine theta is h bar. So instead of sine theta, I can write h bar over, I can write h bar over y bar. Right? So instead of sine theta, I can write h bar over y bar. Instead of sine. So sine theta times this integral divided by h bar times a. Now all I need to do is to simplify right now. You get rid of this h bar because both of them are in top. So you get that. You get I x bar plus a y bar squared divided by a y bar. Right? Now divide it, so you get the first step I x bar divided by y bar a. Right? I x bar divided by y bar a plus the second one, you get what? Just y bar. That's the final result. So here I'm going to just summarize. You can replace that effect. So let's say that's centroid of your geometry. And this distance is y bar. From there to the centroid is y bar. And then this is the total force. Replace one F total. This magnitude was what? Was gamma h bar times a. And the location that it is acting on, y tilde, from here to here is y tilde. Y tilde is equal to y bar plus I x bar divided by y bar times a. There you go. That's the final formula. Right? That's the final formula that you have. And this is the surface of water. That's the surface of water. So this is P0. So look, let's look at it one more time. That's the plate that you look at it from the side, right? And you see, that, let's say this is centroid. So that is the depth of your centroid. Here, from here to the surface is your h bar. If you put it in the formula, you get F total. Now the location that is acting, this is not going to go to, from here to here is y bar. The location is not y bar, it's y bar, look, plus a little bit shift. You see these pieces? Your shift. It goes a little bit down. You see that? How much it goes down? I x bar divided by y bar a. So that's a mathematical proof for experiment. If you go to lab and you see you put that razor at some point, it's below the centroid. How much below? I x bar divided by y bar a. So that's it. These two formula in the test, we have this, and I'll also give you the table for moment of inertia and centroid for different shape. And I ask you to find the location of resultant force on a plate. All you do, you compute these values, but in order to get this value, you really need to understand the proof. How I got this. You cannot memorize. You really need to understand which one is which to substitute in that formula. Right? Okay. So let's solve some problem. At least we can do one problem right here. Most of these equations are in your book. Most of these two equations are in your book. So problem, let's solve problem number 2.9. We have 3 minutes. You know, I was planning to put this in a slide and show you the slide, but the problem in the slide is kind of like immediate memorization because you just see the answer, right? Unless I just show you the problem one slide and then wait on you and then show you the next slide, the solution. I don't want you to just see the problem and see the solution. I want you to think about it a little bit and then see the solution. Now this is problem 2, example 2.9, and this page 68. So basically you have a tanker, and there is a circular window, and you want to see the diameter of this is 2 meters, and the centroid of this guy is submerged at the location 3 meters. So the entire thing is filled with water, for example, right? Is it water? Yeah, it's filled with water, and you want to find the force acting on this window. So this is made of glass. If you look at it, the photo here in the board, and if you fill it with water, there is some forces coming water and pushing it out, right? If you have too much water, it's going to break it. We want to find the magnitude of the force acting on that window. How do you get that? This relation. And also the location. The location of that acting on that. Where is the location? Well, it's not the centroid, right? It's a little bit below the centroid. We just discussed it there. So how can I compute it? Well, just use this formula. The magnitude of the force, F total, is equal to gamma H bar A. Right? So gamma, you put rho G, so rho 1000 G 981 times H bar. What is H bar? The height of the centroid from the level of the water. If we assume the water is all the way to the top, that distance all the way to the centroid, so it's 3. Right? H bar is 3. Times the area. What's the area of that window? Pi. The radius is squared. The radius is 1 squared. That's it. Right? Very easy. Now imagine if you wanted to do this double integral. You should have taken double integral over a circle. Right? In fact, in your code, there is a section to do that. And I will give you homework to do that. But leave it in the exam, I'm not going to give you double integral. All right, so F total and then the location, y cubed, this relation is equal to y bar plus I x bar over y bar a is equal to, what is my y location of the centroid from the level of the water? 3 plus Ix bar. Ix bar, look at this circle, is the moment of inertia of a circle with respect to its centroid. The x bar passing through the centroid. Now you go to the table of moment of inertia, you see that for that, in the test I give you in the appendix in your test. You go to the appendix, you see there are different shapes, rectangle, circle, triangle. For circle, Ix bar is what? Pi over 4, r to the 4th power. You don't need to memorize. Never memorize. It's always in the hand. Right? So plug in. Plus pi over 4. What's my radius? 1 to the 4 divided by y bar, which is 3 times a. What's the area of that? Again, we have the pi 1 square. That's it. Question? Next class we are going to solve more problems. We're not going to leave this section, we have to solve it for more problems.